And so today we're going to be talking about internal energy and heat capacity, and then we're going to, next time, really cover a lot of ground. So you definitely want to download the notes this week and start looking at Wednesday's notes today. Today's material is pretty easy. It introduces internal energy and heat capacity, but then once we hit Wednesday, there's a chunk of material that you want a little bit longer time to look at. So get ahead of me a little bit this afternoon and tomorrow. So one of the most important properties of material that we measure on a daily basis, that we experience on a daily basis, is heat capacity. And as things come to the same temperature, they come to thermal equilibrium, it takes a different amount of joules in each material to come to the same temperature. And that seems strange, but if you put your hand on an insulating material, something that's not very dense, it doesn't take a lot of joules to bring that material up to the same temperature as your body. So it quickly reaches your body temperature, and then it doesn't take any more heat away from you. Okay. And then other materials will take quite a lot of joules to come up to the same temperature. And so we'll discuss when we get to the sort of macroscopic thermodynamics, the thermodynamic definition of temperature. But I'll tell you right now, it's just when two objects are in thermal equilibrium, they share a common property. That's what they call the zeroth law of thermodynamics. When two objects are in thermal equilibrium, they share a common property. And that property is what we call temperature. So when two objects are in thermal equilibrium, they're at the same temperature. So we don't use energy to decide if something is equal material to material. We use temperature. This is what we mean by temperature. If something has the same temperature and it's in thermal contact, it's in thermal equilibrium. There is energy flowing back and forth between the two objects, but the rates are the same, just like in chemical equilibrium. The forward and reverse reactions are happening at the same rate. And two objects in thermal equilibrium, joules are flowing back and forth through collisions and contact, and there's no net change. They share temperature. And so this is the beginning of applying the material we thought about in the last few sections on molecular rotation and vibration and so on. We're now applying it to thermodynamics. It's the statistical part of thermodynamics. And so the Boltzmann distribution tells us about the statistics part, and then the thermodynamics connects it to all of the energetic properties that we're familiar with. And so this initialism called USHAG and K. So the internal energy is U, the entropy is S, enthalpy is H, Helmholtz free energy is A, and the Gibbs free energy is G. And so these are all vocabulary words on this week's homework. And then we have the heat capacity, CV and CP. The subscript V and P mean constant pressure or volume conditions. And so you have different heat capacities slightly, if it's in a constant volume chamber or if it's at a constant pressure with an open chamber. And then we end up with the equilibrium constant. So if we have two systems in thermal equilibrium or thermal contact, they will reach equilibrium, and we can use these statistical tools to tell us where the equilibrium will lie. So it's one of the most successful theories because it got us all the way to the equilibrium constant. So we now know, if you think about that, we could start with atom positions in making molecules of reactants and making molecules of products, and we can put those in contact with each other and compute the equilibrium constant from first principles. That's impressive. It's just that the calculations are too big. They take too long. You think about all the molecular vibration, rotation, electronic cloud that tells us where those vibrational frequencies are. To do that for large amounts of molecules, we could probably get by with doing it in the gas phase. And so in Gaussian, we could calculate equilibrium constants for gas phase reactions. But when we get to solids, the systems are just too large. But we know the science behind it. And so we can start to get to what they call atomistic models for material properties. So this statistical thermodynamics is how we calculate the thermodynamic properties if we wanted to start from first principles. And so to this lecture, we're going to really just focus on the internal energy and the heat capacity. And next time, we'll do the entropy and all the others. Okay. So let's just drill down on internal energy and on heat capacity. So the internal energy, we've already calculated it on a two-level system with and without degeneracy. And there's some more practice calculations like that in the homework. And so it's just those energies of those quantized states times the probability of each of those. So this is the energy for state I, and this piece is the probability for state I. And so you take the probability in being in state 1, multiply by the energy for state 1, and then add that to the probability of being in state 2, and add that to the energy of state 2. So you just look at all the probabilities, that population probability, and then you add in the energies. It's just the expectation value for the internal energy. Now this is a decision point though. You only use this formula if you can count the number of energy levels. So there's really two ways to do this problem. If you're given a two-level system, this is the equation that you use. If I say calculate the internal energy for 3 moles of helium at room temperature, you don't use this equation. Okay. You have 3 moles of helium, yeah. And how many states do you have? Well, the translational partition function is enormous, right? But it's also at room temperature. It's really hot. And so this next, well, actually, let's, before we go on to the 3 moles example, let's take this. And if we know the partition function and we know the internal energy, then look at how we can calculate all of these others. So this is the equation for the entropy. And you see the partition function there? It's the R ln Q. And it's the internal energy divided by temperature. And so it just builds. So once we find the partition function, we can solve for the energy. Once we have both of those, we can solve for entropy.
What's the R constant?
That's the gas constant.
Right.
Yeah. Yeah. I'll go ahead and write it in here. So this will be and then once we have the internal energy and the temperature, we can get enthalpy. Okay. And then once we have that same thing, we could, and the entropy, we could get the Helmholtz free energy. That's A. So this one is Helmholtz. And it is analogous to the Gibbs free energy, only it's at a constant volume. So in chemical engineering, when they have a 300-gallon reaction vessel and the pressure is going to go up or down dramatically, they use the Helmholtz free energy to determine if a reaction is going to be spontaneous or not.
So it's a little bit more simple.
Yeah, so there's just 2 different cases. One uses the heat capacity constant pressure and is a constant pressure free energy equation, and that's the Helmholtz free energy. So if you're a chemical engineer, you're probably going to use the Helmholtz free energy, not the Gibbs free energy. In academia, we use the Gibbs free energy because we have constant pressure apparatuses. All our glassware is open to the atmosphere. And so we have a variable volume, but we have a constant pressure.
But this one is for the
constant volume. Yeah. So there's 2 situations, right? You can have a sealed vessel and let the pressure go up really high. And that would be the Helmholtz. You could see how that spontaneity depends upon pressure. And then in Gibbs free energy, which is the next one, G equals H minus Ts, you could calculate the spontaneity in a constant pressure situation where volume is variable. And so those are all of, when I say USHAG, this is all of the equations that I'm talking about. So when I say here's the 2-level system, calculate USHAG, you can calculate every one of those for a 2-level system. And then I may ask you to calculate a 2-level system, you know, in the homework I ask you, calculate it for a 2-level system and then calculate it for the same 2-level system but with degeneracy in the upper state. And so you calculate all of these again for the upper state. And then I say, now put these in thermal equilibrium with each other. Treat the one with degeneracy as the products and one without as the reactants, and see which side the equilibrium lies. So you just put them in contact, and you can calculate delta H, delta S, delta U, delta G by just taking the products minus reactants. So that's what I would say, start working on that today, because that's going to be the big problem on the test a week from today. And so it's not that bad, but it's pretty tedious, and so you've got to be pretty quick. And then there's also an example on the homework. So there's 2 or 3 problems that I've assigned this week that you could work on, and then we'll answer questions in class. Y'all can work on it together. You can shoot me emails on any of those. Okay. So we're still just focusing on the internal energy and on the heat capacity. So we talk about this condition called equipartition of energy. And this is one of the concepts that I really emphasize on the homework. What do you think that word? Let's take that word apart. Equipartition. Equal parts. You see equa for equal and partition, parts. What does that mean, the parts? What are the parts in this situation?
Microstates.
Yeah, the microstates, or just this, where the molecules are in their energy levels, or particles, you know. So there's really no difference. Even though they may be at different energy levels, statistically, they're so close together relative to the temperature that there's no difference in an excited state or a ground state. And so we're treating all the states as equal probabilities. Think of a 2-level system at really high temperatures. The probability of being in the excited state and the ground state approaches 50-50. Okay, so that would be an equipartition condition, where you have they're equally partitioned between the upper state and the lower state. So this is the case for high temperatures. So when you hear equipartition, think high temperatures. And in most cases, for vibration, for translation and rotation, for those two, room temperature is an equipartition condition. So for rotating molecules, translating molecules, there's really no difference between rotating at J equals 1 and J equals 2 and J equals 3, because you're at room temperature. And so you've got a lot of molecules in the excited rotational states. And so these are the equations for internal energy in the equipartition situation. What happened? Okay. Yes. So for translation, when volume is much, much greater than the thermal wavelength cubed, and that's almost all the cases, right? Thermal wavelengths are down on the sub-angstrom level, and so if we're in a viewable volume, you can see it, then you've got a situation where you're in an equipartition condition for translation. And so the internal energy is really easy. It's that. 3/2, number of moles, gas constant times the temperature. No summation, no probabilities of levels. You just write out the internal energy for translation as 3/2 RT times the number of moles you've got. So the translational energy for 4 moles of helium at room temperature, you put room temperature in there, 298, multiply by R, you have 4 moles and 3/2. So that tells you. A lot of times we just write it in terms of R. Okay. We'll do some of these ourselves in a second. Rotation. When the temperature is much greater than the rotational temperature, and remember the largest rotational temperature was hydrogen, and I think it came in at like 60 Kelvin.
64.
Yeah, 60 Kelvin. So we're way above 60 Kelvin. And hydrogen has the highest rotational temperature. So for all rotation of molecules, room temperature is going to be an equipartition condition. So you can write out 3/2 RT for rotation. So if I ask you what the heat capacity contribution from rotation is for water, then you could just take 3/2 in RT for water. Yeah. Now there's one thing. What about a linear molecule, though? If it's 3/2 for a nonlinear molecule, what do you think it is for a linear molecule?
Just 1. 2/2.
Yeah, 2/2. Yeah. So for linear, it's 2/2 in RT.
There's only 2 rotations.
Yes. Yeah. And so there's 3 translational degrees of freedom.
Yeah.
and there's 3 rotational degrees of freedom in a nonlinear molecule. And so you get a 1/2 RT for every one of those degrees of freedom. Okay. And then for vibration, whenever the temperature is greater than 10 times the vibrational temperature, then you have active vibrations. Now this is a difficult thing. This is where the ambiguity comes. Because in a molecule like toluene, the bending of the whole molecule may be active. Because it might have a vibrational temperature that's, let's say it's 20 Kelvin. So at 298, we're more than 10 times greater than that vibrational temperature. But the CH stretch is 3,000 wave numbers, about 5,000 Kelvin. We're never going to activate that one. So now, we have this 3n-6. Either none of the vibrational modes are active or all of them. So I'm just going to give you those 2 cases where either none of the vibrational modes are active or all of the vibrational modes are active. Because how would you judge? You'd actually have to get in there and see what the vibrational temperatures were for each of the modes. And so I don't expect you to know that off the top of your head for molecules. You'd actually have to get, say, a Gaussian calculation and do that. But if I'm asking you what's the room temperature heat capacity for water, the translations would be active, the rotations would be active, but none of the vibrations would be active. And so it would just be 3/2 nRT for translation plus 3/2 nRT for rotation, and then nothing for the vibrations. Okay. But then if I say what's the maximum for water, then you would add in the vibrations, all 3 of them. So you got to figure out how many degrees of freedom there are, 3n-6 vibrations, and then you would add in an RT for each one of those. And so whenever you're dealing with moles of molecules, or you see the word equipartition, or you hear, at room temperature or something like that, for a real atom or ion or molecule, not just a 2-level system, then you're dealing with an equipartition situation. This is such an easy calculation. It's almost on every GRE chemistry exam or something because it's so simple. Yet the vocabulary words are not. You hear equipartition and internal energy and degrees of freedom, and so the question can be really complicated, but the answer is super easy, right? It's 3/2 nRT for translation, for rotation, and so on. Yes.
Can you say again why you wouldn't use the vibrational energy for water?
Yes. The bending mode is like 1,500 wave numbers. Yeah, and so then you would convert that to temperature, so that might be like 2,000 Kelvin, and we'd have to be at 10 times that, 20,000 Kelvin to activate it. So we have to be at 10 times the yeah, it's not going to happen. Yeah, so even though water does have a bending motion, it's not going to be active. You're going to have to probably be to a molecule the size of naphthalene for that, like if naphthalene's a big board, that bending mode of the whole board. It's a really long molecule, and so that's moving a lot of mass, and so it's going to have a really low vibrational frequency. So the hydrogens, if I'm naphthalene standing on my end, so this is the bending motion I'm talking about. The hydrogens are doing this. 3,000 wave numbers, and the board's bending very slowly. And so you might be able to store heat in that motion. It might have a vibrational frequency of, say, 20 wave numbers, and then at 298, you'd be 10 times that, and so it would be active. But without the numbers, I couldn't be sure, right? So I'd have to give you the vibrational numbers, which would be a long table of all the vibrations, and then you'd have to figure out which ones were active. I mean, that's not too difficult, but at this point, I'm trying to give you the limits. If none of the vibrations are active, what is it? If all the vibrations are active, what is it? You should be able to do that one without any difficulty. Okay. Now, why the vibrations are not 3/2? They say that there's a quadratic component to vibration, and so you get one full RT for each one of those. So now the electronic energy contributions, we've kind of discussed this in the partition function. The electronic energy levels don't contribute to the partition function because we're all in the ground state. same kind of thing. If we're all in the ground state and the excited state electronic level is 20,000 Kelvin higher, then we're not going to be able to store any energy in that without really exciting the molecule. If we were to activate the electronic manifold, what would we be doing? We would be exciting electrons into the upper states. And if it's in a bound state, it's probably going into an antibonding state. And so eventually the molecule is going to dissociate because we're going to fill up those antibonding and bonding orbitals equally, and our bond order will go to 0. And so the molecule will fall apart. So we'll see, maybe it's this next slide. No, let's go right here. Okay. So here's a picture of a diatomic. And at low temperature, we don't have it going all the way down to 0, but we're saying at low temperature, it's just the translations. 3/2 are. And then as we get past the rotational temperature here, then we activate those rotations, and now we have the heat capacity of 5/2 R. Why 5/2?
Because it's a linear.
Yeah, it's diatomic, so it has to be a linear molecule. It's just 2 atoms.
So the two.
Yeah, so it's 5/2 R for, now that's translation and rotation added together. Then once we get past the vibrational temperature, which really it should be 10 times that, then we start to activate the vibrational motions. And now we've got a substantial number of molecules that are excited in the vibrational states, and we have enough energy for them to start accepting heat. And so the heat capacity of this gas goes up to 7/2 R. Okay. And so then that's 5 plus another 2/2, so 7/2 R. And then we do start, if you start to activate the electronic, because that's the only thing left in the molecule, you're heating it up. You start to populate those antibonding, and you see that the molecule dissociates. It starts to go up, and then the molecule breaks apart, and then you end up with 2 atoms. Now, why is 2 atoms have a heat capacity of 3 R? The only thing atoms can do is translate. Okay? So this right here is translational, and it's 2 times 3/2 R. Or 3 R, right? But it's 2 atoms, 2 moles of atoms now, times just their translational heat capacity. And so it's just 3 R. Okay.
So most of the time these temperatures are going to be extremely high to get.
Yes, this is sort of a broad range of temperatures. So we've really heated this molecule up until it completely broke apart thermally.
If you increase the pressure, the temperature drop and do the same thing.
If you increase the pressure.
Well, it's like kind of like you boil water can boil if the pressure's higher
Yes.
at lower temperature. So same idea.
I don't know. I'd have to think about it. Yeah, we're going to get into phase diagrams, and maybe we can tease that thought out when we get to phase diagrams. But yeah, the vapor-liquid equilibrium line, it shifts along, and I don't exactly know how it figures in with the heat capacity. Yeah. But I do know that the molecule has a higher heat capacity, can accept more joules per degree rise in temperature. So this is the slope of energy and temperature. So in this particular case, with the vibration, with the molecule together, it can accept more energy than just 2 atoms in a given temperature unit. So I can put more energy into this gas as a molecule than I can as 2 moles of atoms. This is kind of one of the runaway things that happens in some of the nuclear reactors. So you have water molecule cooling the system, and then as that water molecule started to decompose, then you just had hydrogen gas and oxygen gas. So you went from a very asymmetric molecule, something that has a higher heat capacity, to then 2 moles of gas. And then even then, if you could get it so hot to break apart the diatomics, then you have just it would be 6 moles of atoms compared to 2 moles of water, and it would have less cooling effect. so it could run away. And we saw that a little bit. I don't know if it was exactly this effect, but in the Fukushima reactor disaster in Japan, the cooling level, the water cooling, fell down to expose the fuel elements. And so then it was hot enough, those fuel elements were hot enough right at the meniscus to decompose water into hydrogen and oxygen. Yeah, and so that was a bad thing, because when you're decomposing water into hydrogen and oxygen, it's exactly a stoichiometric mixture, right? Because it came from water. And so then that whole chamber was building up pressure of hydrogen and oxygen in exactly the stoichiometric amount. And then it just needed some ignition source to get it to react again to water and blow the top off. And so you'll see in one of the explosions, it wasn't the nuclear reactor part, it was the cooling pool. Yeah, and so then it just was the atmosphere above that cooling pool that exploded and blew the lid straight off. It was such a symmetric explosion. You saw the lid just go straight off. It wasn't like a Hollywood explosion where you have a point source. It was sort of this, I was studying this because I thought it was amazing. But the lid went straight up, and of course then exposed the immediate area to a small amount of radioactive fallout. So that was just the text of what's going on here. Let's look at a calculation. So y'all do this one together. You can pair up. Let's work on it by ourselves first, and then you can compare your work with your neighbor and see if you got the same answer. So use the Equipartition Theorem to estimate the constant volume heat capacity of ozone at extremely high temperature. So when I say at high temperature or extremely high temperature, I'm telling you to activate the vibrational modes. You might even say the maximum heat capacity of ozone. Let's spend a minute with your neighbor to the left or right and compare your answers. What I'd like for your neighbor to do, and you can do this for your neighbor, is to check to see if you're using the units. Okay? If your neighbor didn't use units, I wouldn't say hit them, but you can berate them. You can. Okay. Well, that's the thing. So this is a molecule. It could be tricky. It's O3.
Yeah.
O3. Yeah, and it's not linear. So this is the thing you would need to know. So that would be one way of writing it. And so since it's a bent molecule, then it's 3/2 R for the rotation. See, this is a good question too. Whenever you have a number of moles, but you're not told how many moles, then just calculate it per 1 mole.
For
Yeah.
1 mole.
Okay,
Yeah.
that's good.
And so you can just leave the units of R as joules per mole, Kelvin, and so then it's essentially per 1 mole. Yeah. So what does this look like? We've got 3/2 for the translation, 3/2 for the rotation, and then 3 vibrational modes that are active, maximum, okay? And so then that's 6R. So you could, sometimes the answers are just listed in terms of R, okay? And so in our Kahoot, it'll ask you various questions, and you just add up how many components go in there and how many R's you have. But let's go ahead and put the units in there. So it's 8.314. It's close to 8. So 6 times 8 is 48. So it's close to 48. I'll say close to 48 joules per mole Kelvin. So it would take 48 joules per mole of energy to raise this substance 1 degree Kelvin. Do you see how that's a heat capacity? It's how much capacity, how much heat it could take before that temperature rises 1 degree. Yeah. And so then different substances have different heat capacities. Okay. A diatomic is going to have less because it's only got 2 halves in the rotation. Yes.
We already multiplied it by the number of moles, so we can cancel moles out.
Yeah, if you did it for 1 mole, it would be essentially per 1 mole. Yeah. So I went ahead and just left it in terms of per mole. Yeah.
If you multiply it by Avogadro's number, you can get it per atom. If you cancel out the moles on the bottom.
You divide it by Avogadro's number.
Or-
It'd be per mole and per mole. So those would go away. And so it'd be, for one atom, it'd be really, really tiny. Yeah. So. Which is funny because you think about, the ionization energy in terms of per mole is an enormous amount of joules, but per electron, pulling one electron off of polymer fiber is not very much at all. That's why you can rip billions of them off by walking across the carpet and dragging your feet. Not a really earth-shattering amount of energy, but you can pull off a billion electrons very easy and charge yourself up. And in the wintertime, I used to have a Suburban with the cloth seats, and I'd get out of that thing and light myself up when I touched the door. I was like, wow, whoa, and it hurts, the nerves. If it all comes out of one tiny spot of your finger, that nerve doesn't like it, So I'd hold my key, and I just use my key, because then the electrons are coming from a bunch of fingers into that metal, and then the metal is sparking to the door. And so then I got a ruler out. I was measuring how far away it was before it would break down. And it was definitely a centimeter. And the breakdown voltage of dry air per centimeter is like 50,000 volts. That's how many volts I was charged up to.
That's
Yeah.
a superhero.
Yeah, exactly. To spark the doors. I got out of my car and I had the key in my hand, and I would just get closer and closer to the door before closing the door, and it would spark back to the door and jump a spark a centimeter long. So then I got on Google. I was like, breakdown voltage for dry air, and it's given in terms of volts per meter, so I converted it down to.
I bet your neighbors will wonder what you're doing.
Yeah, my winter coat with my key getting close to the door. Yeah, it's just fun, So Jennifer and the kids just go in the house. I've been banned from using big words at the dinner table. That's not kidding. I'll use a big word that I don't even know is a big word, and they go, "Oh." Yeah, no. It's like, what? That was a big word. Okay. All right, so let's take a Kahoot where we're gonna work on a bunch of these. So you got to be really quick with them. And we'll just leave all the answers in terms of units of R. So you're really adding up 2 halves and 1 half and 3 halves and all these different halves.
Oh, I'm always going to lose, sir.
All right.
It's the American way.
Sorry for that answer. That was pretty good. So you're running out of room on your phone? So, yeah, that's right. Yeah. I have to delete Twitter or something. Yeah.
You don't already know.
Is it right?
All right, so the code is 109236.
I just like the word. It's the art style. And it's fun.
2 more people. 1 more person. All right. All right, start with something easy. What is the room temperature heat capacity for a mole of helium? So our choices over here in the red are 3 halves RT, blue is R, 3R, and 3 halves R. And we green. Making me nervous. 3 people. 1 person. Oh my goodness, it's a pretty even spread. Okay, so it's green. Yeah, a single atom. All it can do is translate. So you got to think about what species is. You see helium and you're like, oh, it's monatomic gas. Monatomic single atom, no rotation.
I was thinking like,
Yeah.
humanity.
Yeah, okay, yeah. And now this one, 3 halves RT, what is that?
That's the internal energy.
That's the internal energy. So energy, heat capacity. Notice the T is missing. All you got to do, actually, the heat capacity is just the slope of the energy with respect to temperature. So if this is the energy, what's the derivative with respect to temperature?
3 has R.
3 has R, yeah. So it's linear in temperature. Okay, so let's go to the next one. What's the heat capacity constant volume for 4 moles of helium at room temperature? Yay, good job. Okay, so yeah, it's the 3 halves R, and then you multiply by 4 moles. So 4 and a 2, cancel, and you have 2 times 3, 6R. Okay, what's the heat capacity constant volume for 1 mole of carbon monoxide at room temperature? Yeah, room temperature. Vibrational frequency for carbon monoxide that you guys analyzed last semester was in the 2000 range. Nope. I hate it when you know the answer and you just punch the wrong color for whatever reason.
Not too bad.
One person. Make your choice. Okay, majority got it right. 5 halves R. Okay, very good. It's a linear molecule because it's diatomic. It has to be linear. Okay, so what's the CV for 1 mole of water at room temperature? 1 mole of water. Get vibrational frequency for the bending modes, 1500 wave numbers. Probably a vibrational temperature of over 2000 Kelvin. Okay, pretty good. The 7 halves isn't right because it's not linear. Okay, it's going to be a nonlinear molecule, and so then we have translation and rotation only.
Yeah.
Yeah. And so then we have. Oh, someone was on a hot streak. What is the maximum CV for 1 mole? Maximum CV for 1 mole of water. So when I say maximum, what are you going to do about that? And so this will be a great study tool too. You guys can go back and verify why the answers are what they are. Just make yourself a Kahoot account. Look for CHEM_prof. That's my Kahoot name. It's also my Steam name if you need to. Yeah, absolutely. That's right, yeah. Steam chat. All right, very good, very good. All right, so that's the last one. Dun, dun, dun. Good job, DBH. Okay, well, it looks like we're just right on time. So we didn't get to take those other 2 Kahoots. But go ahead and take them. You know, go to find me on Kahoot, and you can take those to help yourself review. Yes.
I turns out I have an extra